Alright, hi folks. I'm back with part 2 of reading a phylogeny worksheet. In this video we are going to cover questions 6 and 7. As per usual, if you have any questions about what I've discussed in the video, please feel free to reach out to me and I would be happy to explain further or do any research to the best of my ability. Okay. Question 6 states, below are photos of hyraxes, an elephant, and a mouse, as well as a more extensive phylogeny that represents their evolutionary relationships. Explain why this phylogeny is surprising given the morphology, or physical form, of these animals. Include the following terms in your explanation. Most recent common ancestor, diverged, analogous trait. Okay, so if we're looking at this, hyraxes are furry. Mouses are furry. But animals, elephants really aren't all that furry. So let's just keep that in mind before we take a look at this phylogenetic tree. Something that I like to do if we're provided with pictures is make a little list of traits that are kind of similar between what we're seeing here. So if you want, you can write below mouse and hyrax furry, and you can write below elephant not furry. Okay, so we will revisit that in a moment. So if we're looking at this phylogenetic tree, it looks kind of complicated, and I know that I was a little overwhelmed at first when looking at this because I didn't exactly know where to start. But again, let's work from the right to the left. So what are we dealing with here? We're dealing with a mouse, a hyrax, and the elephant. So if you want, you can, I know this is what I'm doing, I am going to circle the most recent common ancestor between a mouse and it looks like a hyrax and Asian elephant, which is the first common ancestor ever on this phylogenetic chart at 105 million years old. Let's not even worry about time right now, but we can give that a circle because that's the most recent common ancestor between a mouse and a hyrax and an Asian elephant. Okay, so next, a hyrax and an Asian elephant. Let's circle, and an African elephant. Let's circle the most recent common ancestor between them, which is going to be at about like 55 million years old, kind of roughly. Okay, so this is surprising, right? Because mice and hyrax are both really furry, but it looks like their common ancestry is it's 105 million years old, whereas hyraxes and elephants have common ancestry that is 55 million years old. So elephants and hyraxes are more closely related than mice and hyraxes. And so that's surprising because both hyraxes and mice are furry, but elephants really aren't all that furry. And so why could this be? We kind of covered the term most recent common ancestor in our exclamation point. In our explanation. So analogous traits. This is kind of why we see this. So hyraxes and mice probably needed fur for different reasons. It looks like hyraxes are kind of pictured in this chilly environment, so they probably needed it to keep them warm. And mice obviously use fur for the same reason, to keep them warm, but they don't necessarily have a common ancestor. So that means that this is a analogous trait. So they have the similar trait of fur that help them adapt to their environment well, but it is not necessarily indicative of a common ancestor, as we can see from this phylogenetic chart. Okay, and divergent evolution. So this is the idea that two groups of species can evolve different traits, which essentially enable them to survive environmental pressures. So you are going to see hyraxes and elephants kind of, because they share this common ancestor, right? But you're going to see them evolve these different traits due to environmental pressures. Hyraxes are furry, elephants aren't furry, and that's due to those environmental pressures. Hyraxes probably needed fur to survive, whereas elephants, you find them in warmer climates, they probably did not. And so that's a really good example of divergent evolution. Okay, so now let's revisit this concept of million years old. So as we can see from this phylogenetic chart, we kind of have this line, and at first I wasn't sure what MYA meant. I thought it stood for like myosin or another protein. Turns out it stood for a million years old. And so this line, since MYA stands for million years old, is going to be indicative of time. And so what does that tell us? So that tells us that the branch lengths can indicate, maybe how much time has passed, because this really nice line has been presented to us, and the branch lengths are kind of falling on this line, which tells us, kind of what is hypothesized to happen when, right? So phylogenetic trees are never confirmed to be one thing, right? They're only inferences, they're hypotheses, they're not exactly what happened. So branch lengths obviously can indicate time, because this really nice line was presented to us that tells us that. And branch lengths can also indicate genetic change as well. So with branching and nodes and common ancestry and the sister taxa, we're going to see a lot of genetic change happening. And so branch lengths can be indicative of that. Geographic distance. So not necessarily, branch lengths do not indicate this. It's just not how phylogenetic trees work. And number of fossils discovered. No, not necessarily. Branch lengths are just indicative of time and genetic change. You could have thousands of cat fossils discovered, but the branch lengths aren't indicative of how many fossils are discovered. That's just not how branching is organized on phylogenetic trees. Okay, and that covers all of the mandatory questions on worksheet 2. If you have any questions about the not mandatory worksheet questions for worksheet 2, I've completed them, so feel free to reach out to me if you're curious. But in the meantime, happy studying, stay safe and stay healthy, and if you have any questions about what I've said in the video, don't hesitate to reach out. Bye, folks.